welcome to the session on trusted execution environments. Yeah, it works. Just a second. It should work anyway. Yeah, it works. It works. Okay. Yeah, our first presentation by Joe Bexo is on SGX-Shield, enabling address space layout randomization for SGX programs.
Thank you for the introduction. My name is Jebekso, and I'm from KAIST. Today, I will introduce my recent work, SGX-Shield, that is a system to enable address space layout randomization for SGX programs. This is a joint work between KAIST, Purdue, and Georgia Tech. Nowadays, cloud is a big thing. Many services like email, financial, health, and even government services adopt cloud for the convenience. However, the confidentiality of the data from the cloud provider is not guaranteed, and this security problem is a big concern. Some news articles reported that some cloud providers steal their clients' data, and some hackers uploaded the user data stolen from the cloud in their Twitter accounts. And moreover, some recent researches show that there are many new attack vectors that can weaken or break the security provided by the cloud using only the privilege of guest VM. While this security threat against the data in the cloud becomes more and more serious, SGX that is introduced in the market last year is one of promising solutions. It basically creates a secret region called enclave that is protected from all software stacks, including the kernel and the hypervisor. In other words, even the kernel cannot access this region. And it also resists against hardware-based attacks, such as memory probing attacks, because the CPU encrypts the data when it writes to the physical memory for enclaves. Although SGX successfully denied direct access to the enclave, traditional attacks such as code reuse attacks are still available in SGX. For example, a malicious hypervisor can launch return-oriented programming attacks against the enclave through the communication channel between the enclave and the hypervisor. Address space layout randomization, in short, ASLR, is one of widely adopted technique to defend against code reuse attacks, and it is known to be effective. Because it is important, Intel also includes this in SGX SDK. However, the problem is the current Intel SGX SDK guarantees only limited security. I will explain why it is limited later. But here, I want to emphasize that there are three non-trivial challenges we must overcome to provide the secure ASLR for SGX. The first problem is the memory layout of the enclave is completely visible to the kernel because of the setup process of the enclave. And the second problem is, although we support ASLR, we can provide only a small amount of randomization entropy. And the third problem is, current SGX has a hardware limitation that it cannot support the runtime page permission change. So it has a conflict with the ASLR. So as a result, it becomes defenseless against code injection attacks. To solve these problems, we first designed secure in-enclave loading that hide the memory layout of enclave program from the kernel. And second, we designed fine-grained ASLR to increase the randomization entropy. And finally, we designed software-based permission enforcement so we can enable the runtime page permission change using the software-based permission. I will explain each of them step by step in next slides. First, we must hide the memory layout of enclave from the kernel. I will explain why it is visible to the kernel first. It is because mainly when we set up an enclave, it requires link 0 instructions. So the user process must request set up an enclave to the kernel. Then kernel create the enclave and set up the base memory state of the enclave. And in addition, during this setup process, it also loads the enclave program. So it becomes completely visible to the kernel. And then after finishing the initialization, the CPU guarantees the confidentiality and integrity. However, as I explained, the memory layout is completely visible to the kernel. In the current Intel SGX SDK, it randomizes only the base address. However, it is also known to the kernel because the creation of enclave, the instruction for creation of the enclave is executed by the kernel, and it requires the base address as a parameter. So kernel can get the information, and as I explained, the memory layout is completely visible. So as a result, although the SDK conducts ASLR, but it is actually not random, but completely known to the kernel. To solve this problem, we designed secure in-enclave loading. The basic idea is when we set up an enclave, we only load a dynamic loader into the enclave. And then after finishing the initialization, at the time the confidentiality and integrity are guaranteed by the CPU, we can load the real enclave program from a secure channel. And then we can conduct the randomization inside the enclave. As a result, we can hide the memory layout from the kernel. And the second problem we must solve is, although we support ASLR, we can provide only small amount of the randomization entropy. This is because the current SGX hardware provides only small amount of physical memory, and the virtual to physical mapping is managed by the kernel, like the traditional paging mechanism. So in the view of the kernel, there are only small amount of slot that it can guess there will be some memory object there. So it can try the brute forcing attacks against the enclave. To solve this problem, we designed fine-grained ASLR. The basic idea is split the program into small pieces, and we randomize these objects in fine-grained manner. In user control flow, we expect a program is executed as sequential, in a sequential order, except the case there is a branch. On the other hand, when we conduct fine-grained ASLR, since we will move the location of randomization unit into random place, at the end of the previous randomization unit, if it just executes the next instruction, then it will execute some invalid instructions. So we must redirect the control flow. So we insert a jump instruction at the end of each randomization unit. And at the runtime, we must update the memory references correctly based on the randomly moved places. And the last problem we must overcome to secure the ASLR is the hardware limitation that does not support runtime page permission change. Basically, to enable secure in-enclave loading and conduct relocation for the ASLR, we need write to the code pages. So when we first set up the enclave using the hardware-based permissions, we must set some code pages as writable. However, there is no runtime permission change support, so we cannot disable the writable permission from the code pages during all the runtime. So it opened the possibility of code injection attacks. To solve this problem, we designed software-based permission enforcement. The basic idea is when we first set up the hardware-based permission, we set all code pages as both writable and executable. And then after do the secure in-enclave loading and relocation for the ASLR, we can remove the permission, the writable permission, using software-based permission enforcement. So we basically can remove the readable permission, and in addition, we also remove the readable permission, since the attacker can guess the location of, can leak the location of code object using by exploiting the memory disclosure bugs. In our design, we create an instrumentation that is inspired by native client. Because of the time limitation, I will skip the detail here in this presentation, but you can read the paper for the detail. We implemented SGX-Shield using LLVM4 with Clang front end. We mainly engineered the compiler backend for the fine-grained ASLR and for the software-based permission enforcement. And we also implemented a static linker and secure in-enclave loader that is a kind of dynamic loader from scratch. Current SGX-Shield only supports static linking. In our evaluation, we mainly ask 3 questions. First, how effectively SGX-Shield can defend against code reuse attacks. And the second question is, how much overhead SGX-Shield will bring for CPU-intensive workloads. And the last question is the performance overhead for the real-world workloads. To answer the first question, we conduct security evaluation using code reuse attacks. We observed that in the current SGX SDK, the attacker, I mean the kernel, can easily know the location of each code object without any bit to guess. In fact, this is very natural outcome. As I explained, the memory layout is completely visible. On the other hand, in SGX-Shield, the attacker must guess 20 bits for each code object. So SGX-Shield, it means SGX-Shield can effectively and statistically defend against code reuse attacks. In our micro benchmark evaluation, we measured the CPU, the mbench benchmark execution time. It is a CPU-intensive workload. And as a result, the performance overhead was small, as shown in this table. And the configuration with 64-byte randomization unit size with ASLR and software-based permission enforcement is reasonable because the overhead is less than 7%. And here I want to emphasize that in the future, when Intel introduces the next version of SGX, it will provide the dynamic permission change. So we can just eliminate the software-based permission enforcement. So the performance will be around 1% in that case. And in real-world application evaluation, we use a sample HTTPS server that is provided by Embed TLS. The performance overhead was less than 3%. So we can conclude SGX-Shield brings negligible performance overhead in real-world application. In summary, we aim at designing ASLR for SGX. We met several non-trivial challenges. So we designed secure in-enclave loading and fine-grained ASLR and software-based permission enforcement. As a result, SGX-Shield effectively defends against code reuse attacks with negligible performance overhead. Thank you so much, and now I will take your questions.